here to speak to us about chronic exposure to neonicotinoids and honeybee health. Nadia?
Thank you very much. So neonicotinoids are now the most commonly used pesticides in the world. They're placed into one group because they all have very similar chemical structures and they kind of work in the same way. There have been studies before showing that neonicotinoids do have negative impacts on honeybees, but those were mainly in-lab studies, and they were criticized for not being field realistic. There were also studies that were done in the field, and a lot of those studies actually failed to show any negative effects on the colonies. But were they really field realistic? So one problem that I saw was that those studies were mainly done in canola. Now this is 2013 Canadian map where beekeepers reported colony losses during spring, which is highly unusual, and they thought it was connected to the plantation of corn and the exposure of neonicotinoids. And this is where we grow corn in Canada. So that's why I'm thinking maybe the canola studies are not as relevant, especially to Canadians. And we decided to do our study in cornfields. So what we did is we took a bunch of colonies from beekeepers. We placed half of them near corn crops and half of them far away. So we were at least 3 kilometers away from corn. And we did this in southern Ontario and southern Quebec. We then sampled our colonies to measure the pesticides the colonies were exposed to. And we did a few behavioral tests to see if there was any difference between our near corn and far from corn colonies. We decided to be thorough. So we sampled nectar, pollen, larvae, nurse bees, forager bees, and dead bees. And we also tested 231 different agrochemicals because we wanted to make sure that we're actually getting a complete picture, and maybe it wasn't neonicotinoids, maybe it was something else. And indeed, we found 26 different chemicals in our beehives. Most of them were not neonicotinoids. The most common pesticide that we found was miticides, fungicides. Then we had some neonicotinoids. We had some herbicides and non-neonicotinoid insecticides. Now, just for you beekeepers out there, the miticide is in singular because it was all coumaphos. Now, at least in Ontario, the OBA, the Ontario Beekeeping Association, has recommended to stop using coumaphos and coumaphos products, I think at least 10 years ago. So things like Checkmate Plus. And one of the reasons for that is that the varroa are mostly resistant to it by this point. And it actually really does harm to the honeybees themselves. Also, coumaphos is fat soluble. It stays in the wax for years. None of our beekeepers have used coumaphos in years. And it's still found inside the colony. Because it's fat soluble, it does not. I even read a study where a brand new swarm swarmed outside from a colony that used to have coumaphos in it. The new wax that they have built had coumaphos in it. Okay? It stays inside the fat bodies, it stays inside the fat. So this is just my kind of personal, and especially because the mites are really not, have become really resistant to it. So there's really not a lot of use out of coumaphos. Now, that's a lot of different chemicals, and we need a meaningful way of comparing them. And the way we did it was we calculated the risk. So we took the actual amount that we found in the field, and we divided by the LD50, which is the measure of how toxic the chemical is. It's how much does it take to kill 50% of your test animals. And when we did this analysis, we found that yes, neonicotinoids were the most likely to cause harm to our bees. So from then on, we focused on neonicotinoids. Where did we find these neonicotinoids? pollen. Pollen was the most commonly found neonicotinoids. Dead bees was the second largest category. And I do want to point out that we actually did manage to find some neonicotinoids in the larva, which means that the bees have collected the pollen, they stored it, the nurses ate it, they digested it in their hypopharyngeal gland, and they fed it to the larva, and neonicotinoids survived all of that cycle. Now, since pollen was the biggest category of where neonicotinoids were coming from, we decided to test which type of pollen, where the bees getting this neonicotinoid-contaminated pollen. And what we found that actually the pollen that had neonicotinoids in it came from things like willow, clover, and buckthorn. So these are not commercial crops. They were basically the field margin crops, the wild stuff that grows outside of the cornfield. This is not new. There have been previous studies that show that actually majority of these seed-coated neonicotinoids seep into the system. They are water-soluble. So when it rains, it goes into the soil, it goes into the water, and it gets taken out by the plants outside of the agricultural areas. So the next question was when. So one thing that made our study really strong and robust is we actually sampled the entire beekeeping season. We started early May and we ended at late September. That's the beekeeping here in southern Ontario. So this is what we found. So just on the horizontal axis, that's our different sites. And then it's early May to late September. And the little triangle is when corn plantation takes place. And the darker the blue, the more neonicotinoids we found. And this is what we found. So personally, we were blown away by this. So on average, bees were exposed for 3 months and commonly up to 4 months. So this is inside the colony. So 42 days is actually not outlandish at all. So this also means that multiple brood cycles are exposed to neonicotinoids from egg to death, basically. We also had some neonicotinoids in our faraway sites. Unfortunately, this is not uncommon. Mainly, especially if those sites are next to riverways, downstream from agricultural fields. You can see that right around corn plantation is where those neonicotinoids appear. So that was a lot of work, but I decided that's not enough because all of that is just observational data. People can still technically claim, well, yes, they're there, but they're not doing anything. They're not harming your bees. They're fine. So what I did next is I took all of this information and I designed an experiment in our apiary where I fed our colonies the exact dose and for the duration that we found in the field. And then we tested behavior, and we tested it every 2 weeks for 3 months, which was our average exposure rate duration. So one of the first things we tested was hygiene. The way we did it is we took a brood frame, we poured some liquid nitrogen in there, and then we placed the brood frame back into the colony, came back 24 hours later, and saw how many of those dead brood cells they removed. Those pupa. They removed and threw out. So what we found that in our field studies, towards the end of our study, around September, our colonies that were far away from corn had better hygiene than those that were near corn. And throughout our experiment in our apiary, we found that indeed, as colonies are exposed for longer, the longer they're exposed to neonicotinoids, the worse their hygiene is. Next, we took a look at our queen. So this we only did in our apiary because we had better control of when we took notice if the queen is gone. And what we found again is that colonies exposed to chlorothianidin had a really hard time maintaining a laying queen, and if they lost it, they really had trouble replacing it with a new queen. So we did not introduce new queens, we let them replace their queens on their own. Next, we did a fun little experiment where I took brood frames from the exposed and unexposed colonies. I brought them back to the lab. As single-day bees emerged, I placed little chips on them. And then I placed all of those bees back into a third unrelated, untreated hive. And that hive had a little scanner at its entrance. So when a bee left the colony, it scanned it. And when the bee came back to the colony, it scanned it. And each unique chip had a unique identification number. So I could literally track individual flight patterns. So that was really fun. So a little bit about honeybee flights. There's of course the orientation flights, which are shorter. And there's the foraging flights, which are longer. And we could clearly see this in our data. We had two big peaks. So we separated our flights into orientation flights and foraging flights. So orientation flights, bees that were exposed to neonicotinoids, to clothianidin, they made more orientation flights per day earlier in their life as they started foraging. And as they got older, they took longer foraging flights. Now, you might notice that the red line is a lot shorter than the blue line. And that's because what we found is that age of last flight, which is basically when the bee died, the bees that were exposed to clothianidin died a lot earlier than the bees that were not. And they basically died 23% earlier, which is quite a big hit to a colony, I would imagine. And this is also to reiterate, these bees were only exposed as larvae, because once they were emerged, we put them into untreated colony. So this is, so we spiked a pollen patty, placed it on top of the colony ate it, they fed it to their brood, and then we got that brood and we tested their flights. And we found significant effects. But this is not all. Since we found such a huge mixture of different chemicals, I really wanted to see what would be the synergistic or the combination effects. So what I did is I chose our two most common chemicals that were found with neonicotinoids. One of them was lineron, which is a herbicide, and another was boscalid, which is a fungicide. Now, on their own, we tested them in the amounts we found in the field, and on their own, they killed 0 bees. So then we tested them just clothianidin and just thiamethoxam, which were the two most common neonicotinoids that we found. And this is kind of their LD50, which is, again, the toxicity measure. And this is kind of the average that we find throughout the literature. When we added the herbicide, there was no difference. But we ended the fungicide, the toxicity of the mixture doubled. So now it took half as much of the mixture to kill 50% of our bees. Again, on its own, the boscalid did not kill any bees in this dose. But when you combine it with the neonicotinoid, it doubles the toxicity. So this is also something very disconcerting. So, what is field realistic to all the people that might claim that the lab studies are not field realistic? Well, it's exposure through pollen, it's exposure for average of 3 months, and it's exposure to a variety of pesticides at once. So I would argue that a lot of the lab studies are actually conservative, if anything. We also found that field realistic exposure reduces hygiene, reduces queen replacement, reduces the life expectancy of our workers, and leads to abnormal foraging flights. Thank you all for listening. I'd like to thank our funding agency, OMAFRA and OGS, York University and Université of Laval, and of course my amazing field team, which I would not have been able to do this without. And again, thank you for listening.
Thank you for your work. You showed that a combination of different components make the difference. Do you influence the OECD standard to respect these informations? Because until now they were only tested one component, and the result was that all these pesticides and neonicotinoids would have no influence.
Right, so unfortunately this is something that basically we as citizens have to do. We have to pressure our government to change the pesticide registration methods. So when companies register a new pesticide, they actually test the field mixture they actually put out there. So for example, the neonicotinoid seed coverings, they're patented with 3 different fungicides inside of the mixture, but it's tested individually. So we just have to pressure our regulatory agencies.
All right, thank you, Nadia. Next speaker is Igor Matos. He's going to speak about